Hello and welcome to lecture 20. Today we're going to see if it's possible we might try and do double header, two full lectures. They're not full length, but we'll see what's possible. In this first lecture, I'm going to cover what I call the Chisel grab bag. This is something I've kind of accumulated over multiple offerings of this course. This is the variety of tips of specific aspects about the Chisel language, how to use it, as well as common misunderstandings. After having gone through this entire quarter, you've learned a lot in this course about Scala, about Chisel. And so when we talk about some of these issues, you'll have a lot more depth to kind of understand these conversations. To start off, we're actually going to remind folks about how does Chisel work. And now that you've been using it for, 7 weeks, this isn't a mystery. Yeah, we actually have code again today. Woohoo. Um, Remember what Chisel does, right? So Chisel, we keep acting like its own language. Of course, it's actually just a valid Scala program, right? You've been writing Scala programs all year. So, if you, after this term, if you want to put a Scala on your resume, that's your choice, right? As you've learned, right, if you have a mistake in the Scala level, you're going to compile error, right? It's going to have a compile issue. Um, Scala, is very good at catching this. And so Chisel is just a Scala library, right? Particularly, it's a embedded domain-specific language or embedded DSL. So then, well, what is Chisel? Well, Chisel is this library that's running inside your Scala program. And really, when your program's running, you just are instantiating Chisel objects, right? These are hardware components. They can include even things as simple as a literal, like a for, and of type uint, even something like negating a reference, right? Something like io.in, negating that is an operation, right? So each of these things represents hardware. Those hardwares become, Chisel objects in the program that's running. Every object, of course, internally has inputs and outputs representing the input and outputs of the hardware itself. And all of this is being done kind of under the hood, right? So remember we did things like when we write your own module, we say extends module. Now we know that that's a form of class inheritance. And that module we're extending comes from the Chisel library. And that's what's doing all the stuff. It's kind of hook rolls to kind of get in there, right? And so under the hood, Chisel library is tracking all these objects, all the inputs, all the outputs. So like I said, our code boils down to two things. We either are instantiating things or connecting things, right? So connections, we do the connection operator or the bulk connection operator to two symbols. They are introducing side effects into these Chisel objects, right? They are making connections between inputs and outputs or other things, right? And so really, like I said, your Chisel design is a Scala program that instantiates Chisel things and connects them. And so really all the parameterization I keep talking about and flexibility, that's actually in the Scala program. The Chisel itself is really simple. The Chisel itself is instantiating and connecting, and all stuff around it is a Scala where you can have all the fun. And so really, as you're making your hardware designs, you're thinking about just how do I want to instantiate and connect things appropriately, right? And as you've seen also, of course, if you don't connect things properly, the tools may prune it away. But that's kind of that. So we'll keep going. I'm going to pause for any questions so far. Okay. Um, this is something that comes up in some terms of this course. I want to kind of be very clear about this, right? So hardware designs are static structurally, meaning, it's the same physical hardware, it's the same wiring, same connections. That doesn't change. However, the values on the wires in the hardware can change and when it's, existing in both the real world as well as in the simulation, right? So like I said, so as we build up hardware, the hardware is static, right? We're not going to change the connections. We're not going to, instantiate new hardware midway. All the hardware is going to be in place and fixed before we start simulating or after we finish manufacturing, right? Even something like a mux, which you think of as choosing between inputs, right? The mux always has the connection to both inputs, right? Just a matter of which one it's reading from, right? So the connections are static. The connections are not changing. Um, Meanwhile, wires themselves compare different values or different cycles, right? So, it could be value of 2 this cycle, value of 4 next cycle. But the point is, even though the wire is changing its values, the endpoints aren't changing. And the wire itself actually has no internal state, right? It just propagates from the input to the output. Of course, in the real world, there's some, amount of delay, but in the point of view of this course, when we do cycle level simulation, it's instantaneous. So yeah, a wire can change value, but really, it's not just the wire has value, it's more really just the input it's attached to is changing, right? Because the wire itself propagates that value instantaneously, at least from the point of view of simulation in this course. And then finally, of course, we have state elements, right? Things like a register or memory. They have internal state, and they only change at the rising edge of the clock. At the rising edge, the input becomes the new output and changes the internal state. Otherwise, they do not change. And so in Chisel, we don't even show the clock most of the time. It's kind of implicit. So the result, people sometimes maybe lose track of this, right? But remember, for the most part, things that change in your design are going to change on the clock edge, right? The reason why it's going to be when the input changes, it's going to be when register changes, and everything else kind of holds the value, right? It's going to be continuous, right? The wire has whatever value it's given, stuff like that. Cool. Any questions on that? Great. Okay. So once again, reminding folks about this, stagnance of hardware, right? Um, remember we talked about this notion in Chisel of last connect semantics, meaning that if there's multiple connections to the same input, Chisel must choose a winner, right? This is one of these things where it seems kind of like a runtime behavior, but really it's a static thing. Remember, hardware is static, right? So what does this mean? Well, if the last connection performed in the Scala program, i.e. in the generator, that's the one that wins, right? And that's going to be encoded into a design that does not change, right? So once that generator is run, it elaborates and emits that design. That design is static. It's not going to change. And so as an example of it, think about things like when statements, right? So when statements, semantically people got a good handle on when they think about them, but remember under the hood, they're being done with muxes, right? And so the mux, even though it has the ability to choose between, way 0, way 1, at the end of the day, static connections. So connections aren't changing, it's just which one it's reading from. So here in this example, we connect the output to the input, right? So of course, if I comment this out temporarily, it's just a simple pass through. We've seen this all quarter. I can zoom out so we can actually fit it on the screen. Sure, it passes through. Now, let's say I want to do a thresholding effect, like i.e. clipping. Sure, I can do that too, right? So, hey, you can see the emitted Verilog is pretty clever, right? There's a condition. If iota n is greater than 3, output 3. Otherwise, pass this through. And so if you can see, that's kind of originates, right? Where the default is we pass this through. And then when this condition is true, then we're going to do something else, right? And so you see how the Chisel compiler turned that into a mux, right? To kind of make that play out. If I, for example, omitted this default, it would yell at me, right? Not fully initialized. What do I do when that condition is not true? We, of course, know we could do a dot otherwise for the kind of equivalent of an else. And sure, that works as well. But sometimes the default way of phrasing it's a little bit more clear, right? Whether you do statement and then if or if else, right? Depending on what you're doing, sometimes one makes more sense than the other. But the point is that, yes, it seems like this iota out seems to win over this iota out, but the answer is it doesn't always win. It only wins when this condition is true, and so that's to kind of capture that possibility. The Chisel compiler used the mux. Cool. Questions? Yeah. Okay. The question is, if Chisel targeted an output language other than Verilog, what else could you do? Well, I've talked about it before, and I'm hoping to talk about that again later today. So Chisel technically emits something called Fertile, which is an IR. In the tool flow used in this course, that Fertile is turned into Verilog. In the cutting edge version of Chisel, that Fertile is turned into a different IR called, so it goes to Chisel to Fertile, to another IR called Circuit, and then from there into System Verilog. And so, yeah, it doesn't always have to go, straight Chisel to Verilog. The original Chisel 1, Chisel 2 did kind of go Chisel to Verilog, and starting with Chisel 3, they introduced an IR. So the possibility of having multiple backends became a thing. So I'll talk about that a little bit in the following lecture. Good question. Cool. Okay. So, and the Chisel compiler is pretty clever. So, for example, let's say we have nested whens. So this condition is only going to be true not just when io.in is true, in2 is true, also in1 and in0. So guess what? Yeah, the compiler knows that. It can do the ands for us. We'll figure that out. I'm just showing to kind of remind folks that, all these ones seems kind of very conditional, very transitory, but no, it's static. Um, right? In this case, it recognizes the output is actually going to be, a one hot. It's going to be true, and it's going to do this to AND gate to get there, right? And so, yeah, the hardware is static, right? We have all these things in the program that in the generator are running, but the hardware itself that produces is static. This is when it comes up a lot, talking to students when they have trouble debugging their code, is how do they have the right kind of mutability? So I've been encouraging folks, especially now that we covered functional programming and other techniques, you really need mutability, i.e. var, pretty rarely, right? Um, and what's interesting about this is that Chisel, the library in Scala, can't really tell if you use val or var, right? That's just how way you're writing your Scala programs. And as I've kind of encouraged, you can write your Scala programs more correctly and easier to debug if you use mostly val. Um, so I want to kind of be very, very clear about, don't confuse having mutability in Scala, i.e. val versus var, with your hardware design having different values in the wire, right? I've had students some years say, oh, well, I don't want to have this wire be a val because, it can change values. It needs to be a var so it can change. It needs to be mutable. And it's like, remember, the val and the var are referring to the references in Scala to your Chisel objects. It's not all describing the immutability of Chisel. The Chisel objects, like I said, they're all going to be instantiating hardware. This hardware, of course, can change value over time on a simulation. Um, so, for example, there's some things you can do when you use var that not only can lead to incorrect behavior, but can be sometimes hard to debug or surprising, right? So let's say, for example, you tried to write a counter and you say, oh, I have, you know, a var counter, and then I say counter equals counter plus one. And then you look at the output and you see that it's always one, right? It's always 0 plus one. You realize why, and the reason why, of course, is that you've assigned counter to be 0.u plus 1.u, right? So notice how it's the wrong connection operation here, and there's no register here. It's just, literals. But the compilers won't tell you this is wrong, right? For all it knows, you wanted to add 0 plus 1, right? So, a better way, of course, as you know, is yes, counters you never register, sure. But also by using a value, you prevent this accidental overwriting, because if you try to assign counter down here, it's going to give you an error. You need to use the connection operator. So yeah, please, please, please use val. As an example of how, yet another example of why var can hurt you, reassignments can do weird things, right? And var is allowed at, vals do not. And so sometimes, recognize the common source of errors. The Chisel libraries attempt to do some cleverness to recognize if you've used var and and it does something weird. If you use var in the correct way and it doesn't do anything weird, technically you can't tell and it'll be fine. But I said, you're gonna make a mistake. Humans are fallible. This is gonna happen. So a common bug that I've seen every operating course, but this operating, a little surprised, scratching my head right now, thinking back over the course Slack, is this error message students run into, which is source has escaped the scope of the when in which it was constructed. I don't think anyone posted that on the Slack this term. This is a very common error, and this usually is caused by someone using a var. So the example I had down below is not quite going to cause that error, but it'll show you where things can go wrong. So for now, this code is correct. Just like C, if you write C code that's not buggy, technically it's safe, right? But you make a mistake, you're going to hurt yourself, right? So here we have a wire. We are going to initialize it to IO in, and then we're going to connect it to 0 if it's less than 0. Otherwise, we're going to pass it through. In other words, this is kind of like absolute value, right? So you can see, oh yeah, if it's less than 0, we're going to pass the 0. Otherwise, the same thing. Okay, so this works. If I make this a val, which is what I should have done, it works. Now, let's go back to var. And if I do this, no errors, no warnings, absolutely wrong behavior, right? So now we know what happened, right? That here we have W, which is a wire. It points to that wire object. As the Scala is executing, it now makes W point to 0.s. So that wire init object is floating. It's not going to be garbage collected by the garbage collector. So now W points to 0, And even that notion that this is a conditional operation is lost because of the way we did this. It didn't connect to it properly because it wasn't captured. And so as a result, like I said, you see it just turns into a zero, right? We just lost all this. And so, yeah, if I had a val here, it would tell us this is dangerous because I'm reassigning. Because yeah, when you have chisel objects, you usually don't want to reassign. Usually you want to connect them. And so once again, please, please, please use val, router, and var when you can. Cool. Questions? Okay. So um, in a few places in this course, I've encouraged people to use immutable collections, since just like var, I haven't outright, prohibited them, but I think, use them sparingly. We use them a lot, for example, in the game of life in homework 3 because we hadn't covered functional programming yet. But now that you know functional programming, you know ways to kind of work on collections, and rather than mutating a collection, you can kind of generate a new collection of the new values you want with things like map or .tabulate to populate a new seek and that kind of stuff. If there's some sort of loop carry dependence, you can use something like a fold left or recursion. We've seen that, right? So in both these examples below, we're trying to have a seek or collection of values, 0 to 5, and then we're going to try and increment it. So one way would be to have, okay, mutable array buffer populated with .tabulate, and then just iterate through a for loop. This is kind of probably what you're used to in a lot of classic languages. Um, it uses mutation, which you don't like. It also has iteration, which is kind of a distraction. You're thinking a whole lot about why 0 to 5 and what does that mean? Where does that 5 come from? Versus, using functional programming, you can populate the seek. It's immutable. You can make a new seek, which takes the seek and just adds 1, right? And notice how, way less chance for error. We're not worried about making this 5 the same as that 5. There's no notion of iteration. It's just a map, right? We're saying, hey, take all the elements of that thing and add 1 to them. So both the notions of mutation and iteration aren't even shown, or not necessary in this case, and this is much better. So hopefully I've kind of, sold you out on this material on all quarter, and you're excited about that. Great. Cool. Questions so far? Okay, then one more stylistic thing that comes up is my encouraging people to reduce the number of special cases, right? So I look at some of the code for some homeworks. People sometimes have, like if this parameter equals this, or if this parameter equals that. And sometimes that's okay. Maybe the parameter is like a binary thing, right? That makes sense. Okay, it could be a Boolean. But if it's a sort of numeric thing, it can kind of be tricky. So sometimes we're thinking a little bit about how can you make your code less special casey, more general purpose that has that generality. And one of the things that's actually surprising is you might think that making code super general makes it really complicated. In some cases, making it more parameterized and more general actually makes it simpler. And if you don't believe me, go read, Osterhaus book I recommend a link to in the course, and he has one of his things in his one of his chapters. He talks about this, right? This comes up sometimes in veteran programming. And so, for example, like using a construct like fold left, which has that init value, can work really gracefully with 0 elements, right? It handles that case very well. And yet it can also handle the case of, having non-zero number of elements, right? Which is what you want. If you have a special case, which sometimes occurs, try to keep it to this one. Like, if special case, do something else, regular case. But yeah, sometimes you have this, if this, if else if, else if, else if. You have a lot of else ifs. See if you can't, do something about that. Sometimes people just use this term of, code smell to kind of describe something seems a little bit off in the code and you aren't quite sure what. A lot of else ifs on the parameter is one of the things I'm talking about, where it seems a little bit off and it's worth thinking about what you can do about that. Cool. Um, so sometimes students ask this question, well, we learned both for and for each. You can do a lot of things with those in Scala, but specifically how does impact what you're doing with Chisel? And the answer is actually both can be used in a lot of scenarios. They're both very flexible operators, the way they're designed in the language. Technically, for is a proper operator in the Scala language versus for each is a method implemented on many Scala objects that we happen to be using, but that distinction is pretty minor. So really, it's good to think about the use case and realize technically you probably force one, both in every case, but stylistically there's reasons why it's good to use one or the other, right? And so for both for and for each, when you're actually writing Chisel, usually the goal is to have some sort of iteration and the benefit is some sort of side effect, right? If your goal is to produce something directly, then map is probably gonna be better, right? So for and for each are both when you kind of want iteration or a side effect, right? For me personally, I think for each is great when the collection or range already exists. Maybe you have a vec or a seek or something. Yeah, for each is great. You can kind of iterate through it. If you need to create the range, then for makes a lot of sense. I think people are kind of used to that. Technically, you can create the range and then call for each on that. That's true. You can also iterate on a collection with for. Both are possible. This is becoming a little bit to personal opinion style wise. Yeah, I feel like when I create the range, I like for, and when I have a collection that already exists, for each tends to work for me. But there's some room for there. Now, of course, there are things like zip with index with for each. I made you use that for homework, and I think there's some cases where it makes sense. I think some cases you may see as a little bit cumbersome, right? I think if you're doing for each on its own with zip with index, that's to me kind of cumbersome. I would just do a for of the range. The times I would use it with index with for each is perhaps somehow maybe map or full is going to get in the mix. Without an additional functional operator, I probably would not use that. Cool. Questions? This is another one where in this course, for the most part, we grade on correctness, not really performance, but the computer engineer inside of me can't always stay silent. So um, think about what you're doing with the logic elements, right? CAD tools are pretty smart. Just like compilers, if you do certain things, they will optimize away certain inefficiencies. However, there's certain things that you can do that'll not just make the CAD tool's job easier. It makes it easier for people to read your code, understand it. So, having really inefficient code that you're trusting the compiler to optimize, well, hopefully it's better or easier to read. If it's harder to read, that's not helping anybody. Other times, when you use certain operators, the CAD tools can't necessarily optimize them. So, for example, in a game of life, a common thing I see some years is people use, the mod operation or division operation to get row and column indices from a single number. Um, and, you know, mathematically I can check out, but, in hardware, divide and modulate and remainder mod are extremely expensive, right? Extremely, extremely expensive. And so um, you'd want to avoid that. So, for example, if you're redoing homework 3 and you did that and you wanted to know how could you avoid that, there's a few ways. Number one, use two counters, right? Have one counter for row, one counter for column. Some people have, a single counter and they take the mod and division to kind of get the row and column indices out of it. Just have two counters. That's one way of doing it. Other folks also had the reverse. They had two counters and they turned it back into a single number to use some like multiplication, which once again, maybe if you're kind of clever, you set things up, you can avoid that. So multiply, divide, remainder, these are all expensive in hardware. We want to use them as sparingly or perhaps not at all. Um, Additionally, when it comes time to accessing bits from numbers, uh, when you're writing software, perhaps in C or something, you're used to doing bit shifts or ands to kind of get the bits you want. We don't have to do that in Chisel, right? We can do bit selection, right? We can say, hey, I want bits 6 to 4, or dot head or dot tail if you want to get a certain bit. There's also the ability to kind of combine things with cat. So between using bit selection and cat, um, all these kinds of bit manipulations are easier in Chisel than they are in a language like C. You don't need to use shifts and ands too often, at least not in the way you used to in C for masking and pulling out bits. Cool. Questions? Okay. This is a style point rather than a correctness point, but I think it's worth thinking about both today and also when you kind of write in your code. As I said, hardware is static, right? Like you design the thing, it runs inside the generator. Once that generator finishes, that design is static. It's not going to change. So if you put a hardware instantiation inside of a when block, that hardware always exists, right? It's not going to suddenly vanish when that when statement's not true. The hardware exists, it's static. All the when is going to control is when those connections are active, right? Remember, those connections are always there. It's just the mux, which one is choosing between. So, for example, here we have a counter, and connecting the output to the counter, and we're using enable in this when to decide when to count. So, if I was to go zoom out and you can see the code, you can see that there's some notion of only counting when the enable's on, right? So I think this particular usage is totally fine. However, there are some times where people, I think, put large things inside when blocks that I kind of think this will make the hardware go away or something, and no, it doesn't, right? The hardware always exists. And so, as a style point, sometimes it's helpful to declare large blocks of hardware outside of the when block, which in this case, we can just simply move that line. And this is one of the things that helps people out when they're reading, right? It's not necessarily any more correct, both are perfectly functional. Like I said, this counter is always going to exist, but by declaring it on the outside, we can now kind of make people aware this counter's here. Maybe they may not remember that hardware is always instantiated inside whens, and then the connection's there. Now, what I just did is not quite correct, right? Actually, oh, it is correct, apparently. Ooh, I'm surprised. Files may be buggy. I was gonna say, notice how that we aren't using the enable the way we expect. I'll make that more explicit. I will just toss in enable here, and now it'll work fine. But yeah, like I said, it's one of these things where you put a large block inside of a when statement, large hardware instantiation inside of a when statement. The hardware is always going to exist. Sometimes putting on the outside makes it clear to someone reading the top of the module. Once again, style points, putting large module instantiations at the top of your module kind of makes it clear that this is where the main structure of this module is going to be, and then you kind of can fill in the details as you go through it. Cool. Other questions? Okay. Small point. Remember, I kind of keep pointing out not Chisel, sorry, Scala has a zillion features. It's a rich language, not a minimal language, right? And so, for example, when it comes to bounds and ranges, it has until, which is exclusive, and to, which is inclusive, right? So, just a reminder, right? If I do from 0 until exclusive, 4, I get 0, 1, 2, 3, right? Now, let's say I realize, oh shoot, off by 1 near my bug. You might think to, do this. I should get 4. But I encourage you to, embrace what Scala provides and do that, right? Take advantage of the other keyword. So rather than n+1 and the -1, you often can, use to or until appropriately to avoid the need to do that. Cool. This is one that I don't think I have too many questions during the term, but I'll set the record straight now. So you see my examples, I use sometimes require, sometimes assert, and actually it turns out there's two kinds of asserts, and we kind of glossed over that. So let's address that right now. So first of all, why are there two asserts? There's assert in Scala, which is always been there, and then there's an assert that Chisel adds on top of that. And so what are they? The Chisel assert is something that's for your hardware design. So the way two asserts are differentiated is what is the type of the thing being given as the argument to the assert call. If the type is something that is a Chisel bool, you get the Chisel assert. If the type is a Scala Boolean, you get the Scala assert. So yeah, a Chisel assert is something, remember, this is not synthesizable Verilog, right? This is only going to be in simulation. And yeah, it's going to see, hey, is this Chisel bool true? If this Chisel bool is true, nothing happens. If that Chisel bool ever becomes false, then it's going to cause the simulation to fail because the assertion was failed, right? You can, of course, also give a failure message to your assertions. It's a common practice. Be surprised how industrial users of Chisel, i.e. Sci5, they make so much usage of this assert feature, right? So they'll often make a large module, and then for really testing it, rather than writing just a giant test bench, they'll actually write a test module in Chisel with lots of asserts. And those things will then be used to kind of interact with that. So rather than having a different language, it's the tester has written itself in Chisel, not even Chisel test, but Chisel, and using these asserts to make sure it's behaving the way it expected it to be. Now, the Scala assert is going to not exist in the hardware, right? It's going to exist in the Scala program as it's running during construction, during generation. It's not going to be around by the time you're doing simulation. And instead, you're going to invoke the Scala assert if you have a Boolean Scala type inside those arguments. Now, that's the two types of asserts. So the question, of course, is what the heck is require? Require is a Scala feature. Once again, Scala and all this richness, there's always another feature, another knob. So both require and assert are built into Scala, and they're valid at runtime when your program is running. They aren't static assertions, these are dynamic assertions, right? Your program's running, they check that condition when that statement is called. So what's the difference? The difference is that require, uh, there's a way to disable asserts for a compiled version of Scala. So you can say, hey, I want to build my super fast production binary in Scala that doesn't have asserts. I use the flag to remove them. Requires will not um, be pulled. And so, yeah, it's a way to kind of have removable versus not removable assertions. Stylistically, requires typically are for checking input sanity. In other words, is this the right bounds or range? And if this fails, there's like absolutely no chance it's going to work. Versus assert is for checking internal consistency, right? In other words, has some invariant program been maintained? Sometimes asserts are more expensive to compute, which is why, like I said, you have this option in Scala of having asserts deactivated with a compiler flag. So, as a Chisel developer, where does this leave you? Uh, Chisel asserts are great, both in a testing module, even in the module itself. Like I said, you can put them in your design to your heart's content because they aren't going to be in the final hardware. They'll be in simulation, and so you have tons of them. It might slow down simulation a little bit, but if they're checking useful things, and if your game is correct, you're probably happy you have them. For your generator and just your Scala code in general, you will want to have some sort of assertions to make sure the inputs make sense and that sort of stuff. Technically, you can use require, assert, or both. And yeah, I argue require is great for input sanity versus assert's more for invariance, but that's a style choice. Cool. Okay. So then let's goof around with asserts. So first, why don't I leave just the require? Remember, require is going to be uh, a Scala thing. So has to be at least 0. If I give it 0, a requirement got failed. Okay. Make this an assertion. So it's still going to be a Scala assert this time. It's going to hang the kernel, but so not everything was helpful of error message came out of this, but same thing. And now that I broke everything, I got to restart my notebook. Okay. So that's goofing around with the asserts. Now, note that, okay, let's say I make this back to a require and I don't fail the assertion. So now we actually get a Verilog, right? Okay, it's just a pass-through module, nothing crazy. If we put on this assert, which is a chisel assert, the type here is a chisel bool, comparing chisel objects. We get all this junk, right? What is all this junk? These are all special directives. You know, this is, if not synthesis, i.e. simulation only, it's an assertion, right? So this is a Verilog assertion. Yeah, it's gross, right? But basically, what does it do? It does two things. If this condition is true, and you see it's not just about this being true, but also that we're not in reset mode, it prints out the assertions failed. That's what you're going to see if you're writing this in this Verilog simulator. It also kills simulation. Like, the assertion was failed, it's a kill simulation. So yeah, this is what a chisel assert looks like in terms of the Verilog. Like I said, this is gnarly Verilog. You're happy the tools are writing this and not you. Um, but in fact, the same, right? I, as a designer, could say, you know what? I better not be passing through anything less than 0, and I can kind of check that. Cool. Questions? Okay, so then, uh, you know, we've had this conversation a few times. It's worth kind of coming back to it. How do we think about abstractions, right? What should go in a module versus a function versus a class? We're seeing these different mechanisms for kind of containing and encapsulating our components, right? Um, and you might be thinking, oh, what's the most efficient or whatever? No, no. What's going to make it most clear and easy for humans to understand what's going on and easiest to reuse the pieces you've built and these abstractions you built? The other aspects are secondary, even things like, you might think about efficiency. There's flags to give CAD tools to worry about that kind of stuff, right? You can worry about that later. Get the abstractions and encapsulations such that you as humans can reason about it and you have the reuse that you want possible. So for starters, and this works vast majority of the cases, just using a module per component, that's great. That'll be fine. So what are the other things that can come up, right? We talked about things like classes that are not also a module. There are some scenarios that comes up. Those are pretty specific, right? The common case is, yeah, just make a new module, no problem. When you think about what goes into one of these entities, like I said, number one, think about reuse. Okay, what is the functionality I want to put together where people are going to use this, right? People only want half of this. I should make a module for half of the thing, right? People want two modules and two modules are always used together. Perhaps there's one way you should make a bigger module that encapsulates both of those, right? So think about number one, what's the reuse? Also think about testing, right? Like if you have this massive module, you think, oh my gosh, I can't figure out how to write a test bench, or I'm gonna have to do so many different combinations of things. That should be once again those code smells. You should be worried about, wait a second, that's probably a sign of doing something weird here. How can I break these modules up into smaller pieces and make it easier to do testing, especially unit testing? Um, One phrase you'll see in Osterhout's book, which I'm going to repeat here, is pull complexity downwards, right? To whatever extent possible, any kind of complexity in your design, and some amount of complexity is necessary in order to build things, pull it down, bury it deep inside modules, and prevent people having to understand it, right? Hopefully have a generator that works great. People can instantiate a generator, give it the parameters, plug it in, and they're happy. They don't need to worry about how it works, right? That's what you want. Pull the complexity down, hide it inside these entities. Um, so what are reasons where, I'm saying not to use a module? Sometimes a function that returns Chisel components rather than a class or a module is easier. And the reason why is, imagine like functional construction, using like, functional programming, that kind of stuff. Other times, some people like to kind of merge things together without using modules, whether it be classes or functions, so that the hierarchy they see in the various downstream tools, whether it be the Verilog hierarchy, and waveforms, et cetera, kind of matches what they expect. So some of these lowest level entities, which could be modules, and so they can be dissolved as pieces within a module. Um, that's a style thing. I would do that only if you realize that's necessary and something you decide you want to do. But for version 0, version 1, just make everything a module. Cool. Other questions? This is a really specific point that comes up for some students who are really trying to optimize efficiency of their code. So if you take Chisel and you make let's say a mem, which a mem, remember, is not necessarily SRAM. It could be, a collection of registers, has, asynchronous reads. You do that for a bundle, Chisel's going to make a memory per field of the bundle. And sometimes, for some reasons, you may want to have a single thing. So, for example, if I look at this down here, we have this bundle, which is a 1-bit A field and a 7-bit, um, B field. So what do we get? Well, I say I want 256 of these of this bundle type. Well, I get 256 1-bit things and 256 7-bit things, which, perfectly functional, correct hardware. Um, let's say you talk to your physical design team, they come back to you and say, yeah, I don't want to build a 256-bit, 1-bit wide memory. That's whack, right? And hey, gee, you put these two fields together as 8 bits, that would be way more useful, right? And so, yeah, this is a kind of a hack to get there. Basically, what you do is you say I want a memory of a uint of the width you want. So you get the width of that bundle. And then when you access it, you have to kind of cast that uint back to the bundle type. But that works. So we get this, 256 entry, 8-bit wide thing. Cool. Any other questions? Before we sign off, I want to kind of put a couple announcements out there for folks so we're all on the same page. This week we have both two deadlines. Number one, a initial project checkpoint, so making sure you have a working prototype in the repo. Repo doesn't need to be perfectly complete. Just get something in there working and running. Have both some Chisel, some Scala, and a test to kind of drive it. And make sure in your README you document what you expect to work and not work, and make sure I have access to it so I can see it in order to grade it. The other thing is we had that code review assignment I pointed out to you. So you go log into Canvas, you can see the details. Basically, it's a handful of questions you're looking at. You're going to share code with a classmate. And then let me see what you guys discussed. Usually I assigned you your project partner. If you're working alone, I tried to make pairings across that. There was one group of 3. If I had one group of 3, I did like a cycle. Cool. The other announcement is starting Thursday, we have a series of guest speakers. So we're excited about them. We'll have a guest speaker Thursday as well as next Tuesday and the following Thursday. So we have three guest speakers. We're lucky to have them. They will be remote, but having folks come in person so we can ask questions live would be great. Um, so yeah, we're having speakers talking about a language called Spade, which is basically Chisel in Rust. It's an embedded hardware DSL in Rust. We'll have someone talking about BlueSpec, a long-running hard description language. Has a lot of cool capabilities. They're very unique. It actually has some very different abstractions from what we see in Chisel. It's kind of fun to see the other side. And then we also have session of Chisel formal verification, which is pretty cool. Great. Any other administrative questions? Okay. So yeah, oops.